Over the course of the last 8 years, we've increased computation by 1,000 times. 8 years, 1,000 times. Remember, back in the good old days of Moore's Law, it was 10x every 5 years, 100 times every 10 years of the PC revolution. 100 times every 10 years. In the last 8 years, we've gone 1,000 times. We have 2 more years to go. The rate at which we're advancing computing is insane, and it's still not fast enough, so we built another chip. Hopper is fantastic, but we need bigger GPUs. And so, ladies and gentlemen, I would like to introduce you to a very, very big GPU. Ladies and gentlemen, enjoy this. Blackwell is not a chip. Blackwell is the name of a platform. People think we make GPUs, and we do, but GPUs don't look the way they used to. This is the most advanced GPU in the world in production today. This is Hopper. This is Hopper. Hopper changed the world. This is Blackwell. It's okay, Hopper. 208 billion transistors, and so you could see, I can see, there's a small line between 2 dies. This is the first time 2 dies have abutted like this together in such a way that the two dies think it's one chip. There's 10 terabytes of data between it, 10 terabytes per second. So that these two sides of the Blackwell chip have no clue which side they're on. No memory locality issues, no cache issues. It's just one giant chip. When we were told that Blackwell's ambitions were beyond the limits of physics, the engineer said, "So what?" And so this is what happened. And so this is the Blackwell chip, and it goes into 2 types of systems. The first one is form-fit-function compatible to Hopper. And so you slide and you push in Blackwell. That's the reason why one of the challenges of ramping is going to be so efficient. There are installations of Hoppers all over the world, and the same infrastructure, same design, the power, the electricity, the thermals, the software, identical, push it right back. And so this is a Hopper version for the current HGX configuration. The second Hopper looks like this. Now this is a prototype board, and this is a fully functioning board, and I'll just be careful here. This right here is, I don't know, $1 billion. The second one's 5. It gets cheaper after that. So the way it's going to go to production is like this one here. 2 Blackwell chips and 4 Blackwell dies connected to a Grace CPU. The Grace CPU has a super fast chip-to-chip link. What's amazing is this computer is the first of its kind where this much computation fits into this small of a place, but we need a whole lot of that of Hopper. Overall, compared to Hopper, it is 2.5 times the FP8 performance for training per chip. It also has this new format called FP6, so that even though the computation speed is the same, the amount of parameters you can store in the memory is now amplified. FP4 effectively doubles the throughput. This is vitally important for inference. The amount of energy we save, networking bandwidth we save, the amount of wasted time we save will be tremendous. The future is generative, which is the reason why we call it generative AI, which is the reason why this is a brand new industry. The way we do it is fundamentally different. We created a processor for the generative AI era, and one of the most important parts of it is content token generation. We call it, this format is FP4. That's a lot of computation. 5x the token generation, 5x the inference capability of Hopper seems like enough. But why stop there? And so we would like to have a bigger GPU, even bigger than this. And so we decided to scale it. So we built another chip. It's just an incredible chip. We call it the NVLink switch. It's 50 billion transistors. It's almost the size of Hopper all by itself. This switch chip has links in it, each 1.8 terabytes per second. What is this chip for? If we were to build such a chip, we can have every single talk to every other GPU at full speed at the same time. That's insane. And as a result, you can build a system that looks like this. This is what a DGX looks like now. Remember, just 6 years ago, I delivered the first DGX-1 to OpenAI. That DGX, by the way, was 170 teraflops. That's 0.17 petaflops. So this is 720. And so this is now 720 petaflops, almost an exaflop for training, and the world's first machine in one rack. Just so you know, there are only a couple, 2, 3 exaflops machines on the planet as we speak. And so this is an exaflops AI system in one single rack. Well, let's take a look at the back of it. So this is what makes it possible. That's the back, that's the back, the DGX NVLink spine. 130 terabytes per second goes through the back of that chassis. That is more than the aggregate bandwidth of the internet. We could basically send everything to everybody within a second. 5,000 NVLink cables. In total, 2 miles. Now this thing, if we had to use optics, we would have had to use transceivers and retimers, and those transceivers and retimers alone would have cost 20,000 watts. 2 kilowatts of just to drive the NVLink spine. As a result, we did it completely for free over NVLink switch, and we were able to save the 20 kilowatts for computation. This entire rack is 120 kilowatts, so that 20 kilowatts makes a huge difference. Cooled, what goes in is 25 degrees C, about room temperature. What comes out is 45 degrees C, about your jacuzzi. So room temperature goes in, jacuzzi comes out. 2 liters per second. We could sell up 600,000 parts. Somebody used to say, you guys make GPUs, and we do, but this is what a GPU looks like to me. When somebody says GPU, I see this. 2 years ago, when I saw a GPU, it was the HGX. It was 70 pounds, 35,000 parts. Our GPUs now are 600,000 parts and 3,000 pounds. Okay, so 3,000 pounds, ton and a half. So it's not quite an elephant. Now let's see what it looks like in operation. If you were to train a GPT model, 1.8 trillion parameter model, it took about 3 to 5 months or so with 25,000 amperes. If we were to do it with Hopper, it would probably take something like 8,000 GPUs, and it would consume 15 megawatts. 8,000 GPUs and 15 megawatts, take 90 days, about 3 months. If you were to use Blackwell to do this, it would only take 2,000 GPUs. 2,000 GPUs, same 90 days, but this is the amazing part. Only 4 hours. So from 15, yeah, that's right. Blackwell would be the most successful product launch in our history. And so I can't wait to see that. We take all of the data, we put it into a system like DGX, we compress it into a large language model. Trillions of tokens becomes billions of parameters. These billions of parameters becomes your AI. So I just described in very simple terms, essentially what just happened in large language models, except the ChatGPT moment for robotics may be right around the corner. And so we've been building the end-to-end systems for robotics for some time. I'm super, super proud of the work. We have the AI system, DGX. We have the lower system, which is called AGX, for autonomous systems. The world's first robotics processor. When we first built this thing, people are, what are you guys building? It's an SoC, it's one chip, it's designed to be very low power, but it's designed for high-speed sensor processing and AI. And so if you want to run transformers in a car, anything that moves, we have the perfect computer for you. It's called the Jetson. And so the DGX on top for training the AI, the Jetson is the autonomous processor, and in the middle, we need another computer. We need a simulation engine that represents the world digitally for the robot, so that the robot has a gym to go learn how to be a robot. We call that virtual world Omniverse. And the computer that runs Omniverse is called OVX. The computer itself is hosted in the Azure cloud. Okay? And so basically we built these 3 things, these 3 systems. On top of it, we have algorithms for every single one. Now, I'm going to show you one super example of how AI and Omniverse are going to work together. The example I'm going to show you is kind of insane, but it's going to be very, very close to tomorrow. It's a robotics building. This building is called a warehouse. Inside the robotics building are going to be some autonomous systems. Some of the autonomous systems are going to be called humans, and some of the autonomous systems are going to be called forklifts. And these autonomous systems are going to interact with each other, of course, autonomously, and it's going to be overlooked upon by this warehouse to keep everybody out of harm's way. The warehouse is an air traffic controller. And whenever it sees something happening, it will redirect traffic and give new waypoints, just new waypoints to the robots and the people, and they'll know exactly what to do. This warehouse, this building, you can also talk to. Of course you can. And all of this is running in real time. What about all the robots? All of those robots you were seeing just now, they're all running their own autonomous robotic stack. Let's talk about robotics. Everything that moves will be robotic. There's no question about that. It's safer, it's more convenient, and one of the largest in automotive. Beginning of next year, we will be shipping in Mercedes, and then shortly after that, JLR. Today, we're announcing that BYD, the world's largest EV company, is adopting our next generation. It's called Thor. Thor is designed for transformer engines. Thor, our next generation AV computer, will be used by BYD. The next generation of robotics will likely be a humanoid robotics. We now have the necessary technology to imagine generalized humanoids. In a way, human robotics is likely easier, and the reason for that is because we have a lot more training data that we can provide the robots, because we are constructed in a very similar way. It could be in video form, virtual reality form. We then created a gym for it called Isaac Reinforcement Learning Gym, which allows the humanoid robot to learn how to adapt to the physical world, and then an incredible computer, the same computer that's going to go into a robotic car, this computer will run in humanoid robot called Thor. It's designed for transformer engines. The soul of Nvidia, the intersection of computer graphics, physics, artificial intelligence. It all came to bear at this moment. The name of that project, General Robotics 003. I know, super good. Super good. Well, I think we have some special guests. Do we? Hey guys. So I understand you guys are powered by Jetson. They're powered by Jetsons, little Jetson robotics computers inside. They learn to walk in Isaac Sim. Ladies and gentlemen, this is orange, and this is the famous green. They are the BDX robots of Disney. Disney Research. Come on, you guys, let's wrap up. Let's go. 5 things. Where are you going? What are you saying? No, it's not time to eat. It's not time to eat. I'll give you a snack in a moment. Let me finish up real quick. First, a new industrial revolution. Every data center should be accelerated. $1 trillion worth of installed data centers will become over the next several years. Second, the computer of this revolution, the computer of this generation, generative AI, trillion parameters. This is what we announced to you today. This is Blackwell. Amazing, amazing processors, NVLink switches, networking systems, and the system design this is Blackwell. And this, to me, is what a GPU looks like in my mind. Everything that moves in the future will be robotic. You're not going to be the only one. And these robotic systems, whether they are humanoid, AMRs, self-driving cars, forklifts, manipulating